Engineering 305, Chapter 4, Sections 1 through 3, Stress Strain Diagrams and Generalized Hooke's Law. We're combining all three sections into one lecture. The reason for that is it works. This is kind of an intro to our tie-in between material properties and the things we covered in Chapter 2 and 3. And this will allow us to link those together through a set of equations that allow us to convert stresses to strains and strains to stresses, whether they be 2D stresses or 3D stresses. So let's dig into it. The course learning objective from the larger list of learning objectives, number 7 is using the appropriate equations. We're going to demonstrate the relationship between stresses and strain for isotropic materials. We are not dealing with anisotropic materials like carbon fiber yet. There is a section 4.5 on that. We will get there, but this is about doing this for isotropic materials. The equations that we're going to look at, there's actually quite a bit. So we've got our definition of stress, or our definition of Young's modulus, and our definition of shear modulus. And then we're going to be moving on into isotropic materials for plane stress. We've got, I want us to be looking at or be thinking about the material property chart that we were working with in engineering 205, and to be thinking about those things. But then really the big deal, well, not the big deal for this section, not for this chapter, but for this section is going to be these upcoming equations. The plane stress equations, and that is our stress is only occurring in the X and the Y directions. We don't have a stress in the Z direction, but we still have a strain in the Z. So that's going to cause a stress in the X and Y is going to cause a deflection in all three dimensions. And then we've got the generalized case where we've got a stress in all three directions, sigma X, sigma Y, sigma Z, and we get strains then in all directions. So that's the thing that we're dealing with. That's what we want to be thinking about. Funny, I can't erase it. There we go. That's what we're going to be thinking about and working towards in this chapter. So as we start out, I want to talk about this material chart, which, and maybe this section should be straighter, but what we know coming out of this is we got some material properties, and we defined a point here, which is SY or a sigma Y. It's a strength, and the Y denotes that it's a strength or a stress, and it denotes the yield point for the material, where it starts to plastically deform. And so we could talk about this is a plastic region, and this side here, the good side is the elastic region. The difference is once we've gone out of the plastic region, then when we move beyond into plastic, then we don't get all of that moment. It doesn't go back to its original shape anymore. We've lost that forever. Our axes on this plot are stress and strain, and the big thing that we're looking at is this slope here, that rise over run. We are defining Young's modulus, and a definition gets 3 of those as the stress divided by the strain. That's the rise over the run. We'll often present that equation as stress is equal to Young's modulus times the strain, but either one, we're just rearranging that definition. But that is the rise over the run on our material stress chart. All right. Once we have that, then we can start solving. Well, I've got one more thing, one more definition, and that is if we were in person, I would demonstrate with this green TheraBand that when I take an object and I pull on it, then I'm going to get this object, that square is going to elongate. It's going to get a delta L, but it's also going to shrink in the transverse. And I can't spell verse here. V-E-R. It's going to shrink in the transverse direction. And so there's one more material property that comes out, and it's called the Poisson's ratio. And I want to call it the Poisson's ratio, but it's got two S's. So it's Poisson. It's some French guy, right? And that is the negative, and I put a negative in there because when I stretch in one direction, it shrinks in the other direction. So it's negative the strain in the lateral dimension compared to the strain in the longitudinal direction. That is, stretch it in the longitudinal, I pull it in the longitudinal, and I get lateral deformation. And so this is about that ratio. That's what this Poisson's ratio is. And now with these definitions, I'm going to start putting information together. I'm going to start building up some systems. So start that on the next slide. So I'm going to take this block and I'm going to put it under tension, and unfortunately, I'm going to put my coordinate system like this. That's my X, and now this is my Y. So maybe I should have turned that whole block on its side, but we're masters of our domain, of our coordinate system. We can manage that, right? If I want to start looking at the strain in the X direction, right? I'm going to look at that as the stress in the X direction and divide it by Young's modulus, and that's going to give me my answer. And that's going to give me part of the picture. I'm also going to strain in the Y direction as a result of that stress in the X direction. And I'm going to write this out in a couple steps, and then we'll simplify it. Remember, Poisson is equal to minus the strain in the lateral divided by the longitudinal. All right. And so the strain in the lateral, I'm going to rewrite that as minus the strain in the Y direction as a function, or divided by the strain in the X direction. And so now if I want to figure out what the strain in the Y direction is, well, that's going to be equal to minus Poisson times the strain in the X direction. But the strain in the X direction I just solved up above, right? There's a strain in the X direction. So now it's equal to minus Poisson times stress in the X direction divided by Young's modulus. So now in this simple case here, I've got the strain in the X direction, and I've got the strain in the Y direction as a function of the stress in the X direction. Or we can think about it as the force divided by the area in their X. Yep, we got it. So now the question is, okay, we're on the same path that we were on in chapter 2, honestly. We started out with this simple case where I pull on something and I get the one-dimensional results. And we just got the one-dimensional results. A force in one dimension affects both the X and the Y. Remember what we did in chapter 2? Just like good story, there's this parallelism. We now are going to take this and extend it to 2 dimensions. All right. In 2 dimensions, I'm going to have my block, and I'm going to pull on it here, and I'm going to pull on it here. And I'm going to change my coordinate system. I know, maybe I should have been consistent. X, Y. And then these forces are going to be, or these stresses are going to be a stress in the X and a stress in the Y. And if I want to look at let's start out with, well, no, let's start out. We'll just start out with my stress in the my strain in the X direction. Now, with the previous example, you know that the strain in the X direction is equal to the stress in the X direction divided by Young's modulus in the X direction, but Young's modulus is the same in every direction, so I'm going to get rid of that. We also know that in the previous section, I had the strain in the X was causing, the stress in the X was causing a strain in the Y. So I should think that a stress in the Y should cause a deflection in the X. And it does. Do I just add that? If I wrote that down, if I look back, I would add that in like this, times Poisson times the strain in the Y, but the strain in the Y is the stress in the Y divided by Young's modulus. Does that make sense? Because what I'm doing is I'm saying I've got this, and that's from pulling on it in the X direction side, it's horizontal now. And then I've got another deflection from pulling on it in the Y direction. How's that? Can I just add those together? Well, you can, following the principle of superposition, but the principle of superposition has two key assumptions in it. One is that these events are independent of each other. Are they independent? Well, yeah, that's a tough, but that's the assumption we've got to make. And the other one is that these events are linear. We already looked at very briefly this material property curve, and it's a curve, the stress strain curve, and we're saying it has to be linear in order to add it together. So this equation certainly has its limitations, but we're going to work with that. We're going to assume it for almost the rest of this semester. In fact, I'm going to say for the rest of the semester, we're working in a linear region, and that these events, the stresses in the X and the stresses in the Y, are independent of each other. Those are some big assumptions. Once we've written this down, if you follow that far, then you should be able to go, well, what's my strain in the Y? Well, from the last derivation, I had this term first. It's minus Poisson times the stress in the X direction divided by the Young's modulus. But then I have to add in the deflection from the stress in the Y direction divided by the Young's modulus. Now, I can simplify all this and pull Young's modulus out to the front, but this is a valid way of approaching it. And now one more thing that we didn't do in the last time. We should look at the strain in the Z direction. We didn't do that up above. The strain in the Z would be exactly the strain in the Y, because it would only have a component from the X force, because that's all there was. But now the strain in the Z direction is minus Poisson times the stress in the X divided by E, Young's modulus. And that's the strain in the Z from the stress in the X. And I've also got another term, minus Poisson stress in the Y divided by Young's modulus, because now a stress in the Y and a stress in the X create a stress in the Z. And now that one clearly should be simplified. I was playing a trick from another software package. That should be rewritten as minus Poisson over Young's modulus, stress in the X plus the stress in the Y. All right. That actually gets us, it gets us a long way. That gets us, if we rewrite those are my equations 4-4, which are the, oh, sorry, that's not correct. That's not correct. 4-4 is the one-dimensional. We need to go to, I'm not sure which number equations these are. I'm going to just erase that. I know they're going to come off the formula sheet, and we're going to review those in a second, but I'm going to cut and paste those into the presentation so that they're nice and clean and neat. So I think these are actually 4. Is it? No, these are 4-4. These are my 2-dimensional. And then I'm going to get 4-6 and 4-7, which are the 3-dimensional ones. Now, well, I'm going to leave this alone for a sec. No, one more thing to talk about, and that is on a new slide. We just solved for the strain in the ith direction as a function of the stress in the I, J, and K direction. You got to get my notation there. What I'm saying is the stress in the X direction is a function of the stresses in the X, Y, and Z. Or the strain in the X direction is a function of the stress in the X, Y, and Z. Or the strain in the Y direction is a function of the stress in the X, Y, and Z. That's one way of looking at it. What we also might want to do is take that equation and convert it. And the conversion process is a bunch of algebra and substitution. We might want to convert that so that the stress in the ith direction is a function of the strain in the I, J, or K. And what that means is that if we're given stresses, we can convert it to strains. Or the other type of problem we might get is we've got strains and we want to convert it to stresses. We want to be able to do either one of those. So now we'll start looking at the equations that we get, 4.4 through 4.7, where they apply and what's going on and how we deal with them. So these are our 2D equations. You can tell they're 2D because I'm not solving for the stress in the Z direction is equal to 0. It doesn't show up in any of the equations there, and there's no stress in the Z is equal to da, 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 da. So this is equivalent to being on the surface of an object where I'm not imposing a normal or a tension or a compression force on anything. Once I'm on the inside of a structure, then I'm always going to have something pulling or pushing on me in all 3 directions because of Poisson's ratio. That is, once I pull in the X, the material has to shrink, and so it pulls the material next to it. So there's those internal stresses. So that's what we've got. The next equations, these are the 3D equations. And I'm going to say, really, these should look familiar. When we derived it, we had the strain in the X, which is a function of the stress in the X, and then Poisson's ratio related to the stresses in the Y and the Z. And those equations all line up. We're just changing out whether we're dealing with the X or the Y or the Z. And then we go through, what we didn't do is go through a bunch of math to rearrange those to get them into our stresses as a function of our strains. But now we're seeing that there is a stress in the Z direction, and that stress in the Z direction is showing up several different places. So it becomes fairly straightforward to do that. So there you go. Last thing that we should talk about, and not the last thing, the next thing that we should talk about is what are we going to do with the shear? What are we going to do with the shear XY? Well, there's one more material property that we haven't talked about, and that is the bulk, not the bulk modulus, the shear modulus. And that shear modulus is important. It gets defined G gamma xy. I was putting indice notation on it when we're not quite ready for that. The shear stress in the xy direction is equal to G, the shear modulus, which is just another material property. The shear modulus times the shear strain. It is truly a definition. It should be written as G is defined as tau over gamma, and I can put my indices on there, xy, xy. Now, one thing I'll say about that is realistically for the property, for the materials that we're going to deal with, G is the same in every direction. And so I'm going to get rid of this XY notation, and I'm going to say IJ, IJ. And so if I want the shear in the XY direction, it's gamma in the XY, but I could go from shear in the YZ direction and then the shear strain in the YZ direction. It all works out. Now, the last thing that not last thing, didn't I just say that? Last thing, and I corrected myself. The next thing is I want to give you a definition, because these things are not independent of each other, these material properties. The Young's modulus is equal to 2 times 1 plus Poisson's ratio times the shear modulus. That's how we get one or the other. We're going to start with, typically we're going to measure Young's modulus off the stress strain chart. We may measure Poisson's ratio, or we may simply use the 0.3 or 0.29. Think about that. 0.29 to get to where we need to be, and then we calculate G, that shear modulus. We can test for shear modulus. That is a material property test we can execute, but we don't always do that. So there's some example problems I'm going to do, 4.1 and 4.2, and that will button up this section of the textbook. Hope you're doing well.